Hello all and welcome to this course on time series modeling and forecasting using R. So now we'll start with a new week and then a few fresh topics to start with. So again, just to give you a brief overview of what we'll see in this week is we'll focus more on something called as model identification, right? So how do you identify the correct orders of a model, or even before that, how do you kind of identify the correct model which could be placed on some real data and so on and so forth. Right? And then we'll talk about a few other aspects of, let's say, model identification using some information criteria, right, etc. Okay, so let's start. So just to give you a short overview of where we are at this stage is that so far we've kind of looked at several different time series models, right? So if you remember, we covered something called as random walk to begin with, or let's say a very simple moving average, right? Or we talked about white noise, or slightly more advanced processes such as, let's say, autoregressive, moving average, then the combination of AR and MA, which is ARMA, so autoregressive moving average model. And then if the model has a trend, or if the real data has a trend, then one actually needs to model that using ARIMA. So ARIMA means autoregressive integrated moving average. And then of course the last extension that we studied in the last week was seasonal ARIMA. So alongside the trend, if you also have seasonality, or let's say some repetitive nature in the time series, then probably one can't fit a proper ARIMA model for that. So for that you require a slightly advanced technique which is called as SARIMA. Okay. Now the whole question, and then again the important question is that how do you find the best suitable model given any practical scenario or given any practical data? Okay. So essentially what this question is asking is that is, how do you find the optimal orders, let's say P and Q, of a particular model? So again, let's say, so why are we saying P and Q? Because again, let's say if you have an ARMA process, so all of you know that ARMA process kind of depends on two orders, right? So P and Q. And then of course ARIMA depends on three orders P, D, Q. But then again, that middle order D is kind of coming from the number of times you difference the series, right? So essentially speaking, these two are the important ones, right? So P and Q. So how do you identify the optimal number of P and Q, or the optimal lags up to which one should actually extend the AR part and the MA part? Okay. So we'll talk about a few techniques in this regard and so on and so forth. Okay, so now before we start with anything new, I'll again go back to one of my earlier lectures, and then I'll specify and then I'll elaborate more on this particular technique, which is using ACF and PACF plots. Okay. So I'll say this is more of a visual kind of a check, that based on both these plots, let's say ACF and PACF, how do you come up with a rough idea about what orders are true for the underlying AR structure or the MA structure. Okay. Now again, what exactly are the full forms of these two? So ACF stands for autocorrelation function, and then PACF stands for partial autocorrelation function, right? So again, just to quickly summarize, this PACF is nothing but partial, or this is kind of similar to a conditional kind of a correlation, right? So we talked about the expression in one of the earlier lectures, but how exactly do you condition that? So let's say this is something like correlation between, for example, let's say yt and yt plus 2, and then let's say given the intermediate term which is yt plus 1. So something like that. Right? So such correlations are called as partial autocorrelations or conditional correlations, right? And if you vaguely remember, I gave you a description of ACF plots and PACF plots in one of my earlier lectures also, right? So as seen earlier, one can actually find the optimal orders, which are nothing but P and Q of a particular ARMA structure, using both these plots. So specifically using the ACF plot and the PACF plot. So again, probably in the next slide we'll talk more about, or we'll kind of elaborate more using the plots themselves, but then here you see a kind of a revision kind of a table, and the first row tells you that which plot are you having, so either ACF or PACF, and then the first column gives you the appropriate model. So the underlying models are, or underlying choices are, it could be either ARP or MAQ, right? And then what you see inside this table are the tendencies. So let me explain a bit here. So let's say for a particular ACF plot for an ARP model, right, which is nothing but this top left comment here. So again, just to repeat, for a ACF plot for a particular ARP model, you actually see a tailing off kind of a tendency. So, the plot has to tail off after lag p, alright. And then at the same time, if you observe the ACF plot of a MAQ process, it shows a cutting off tendency. So, I would say that cutting off is much more predominant than tailing off, right. So, cutting off means that the correlations abruptly cut off after some lag or after some point, and then tailing off means they kind of gradually decrease, right. And then one can actually observe an exact opposite kind of a tendency when it comes to PACF. So, if you focus on a PACF plot for a particular AR model, it should show a cutting off tendency after lag p, while if you see a PACF plot for a particular MAQ model, it should show a tailing off tendency after lag q. So, in a way, if you observe just for a few more minutes on this entire table here, so whatever happens for an underlying AR model is exactly opposite to what do you observe in a underlying MA model. Alright. Now, just to explain this a step further, so we will take up the actual plots, and then I think I showed this slide in my earlier lecture as mentioned a short while back, but then again probably just to elaborate on how can you actually invoke the ACF plots and the PACF plots for a particular AR model and the ME model. Okay. Now, again this is difference between ACF and PACF plots, so you can actually mention PACF here. So, ACF and PACF because we are analyzing both of them, right, and then not just one. So, difference between ACF and PACF plots for a particular AR model and a particular ME model. Alright, so in front of you again we have 4 plots. Alright, now the first column gives you the ACF plot and the PACF plot for a particular AR2 model. So, we are fixing the order to be 2. And similarly, on the right hand side or the second column gives you the ACF plot and the PACF plot for a particular MA model of order 2, right. So, in general we are fixing the order to be 2 in both the cases for the AR structure as well as the MA structure. And then of course, the top row gives you the ACF plots for both the models, and then the bottom row gives you the PACF plots for the both the models, alright. Now, again one can actually observe the tendencies we listed in the prior table that we just saw, right. So, again just to repeat, now if you focus on the ACF plot for a MA2 model for a second, right. So, ACF plot for a MA2 model, which is this one right here on the top right, then again as discussed in the earlier table, you can actually see a cutting off tendency after lag 2. So, by the way, you should remember one thing, that the x axis on each of these 4 plots shows you the lag, right, and then again this is true for any of these 4 plots. So, on the x axis you are actually plotting the lag, and on the y axis what do you have? So, on y axis you have either the autocorrelation or the partial autocorrelation which is being plotted, alright. Now, let us say that you start at lag 1, so this is lag 1, this is lag 2, this is lag 3, 4, 5 etc. Okay. So, for each lag there will be some correlation because you are finding correlation between let us say yt and yt plus 1. So, lag is 1, right, or let us say if you are finding correlation between yt and yt plus 2, so lag is 2, right, and then hence we can actually get more than 2 lags also. So, let us say correlation between yt and some yt plus 8, right, so lag is 8. Okay. So, one can actually get this plot, I mean just to explain what is going on in this plot, right. So, for each lag I can actually plot the corresponding autocorrelation or the partial autocorrelation. Okay. Alright, so now again coming back to the tendencies, so can you see that so this ACF plot is kind of showing a cutting off tendency after what lag? So, after lag 2, alright, and then since it is showing a cutting off tendency after lag 2, so the model could be MA2 in that case, alright. Now, one more thing is how do you sense that something is cutting off? So, in each of these plots again you can actually see these hypothetical confidence bands which are given using horizontal blue lines in each of the plots, right. So, for example, these lines, right. So, what exactly are they? So, these lines are nothing but 95% confidence bands for those particular correlations, right. And if any of the correlations are outside those bands, then those particular lags would be significant. Otherwise, if the correlations are inside the bands entirely, then those lags are not significant, alright. And hence, if you again observe this plot for a second, can you now see that after lag 2 here, which is shown by the second spike, all the further correlations are really small, so which are not significant, and hence we sense that such a plot is showing a cutting off tendency, alright. And then similarly, on the other hand, if you observe this bottom left plot, which is nothing but PACF for a AR2 model, you can actually see the exact same thing, okay. Now, how do you sense a tailing off tendency? So, tailing off tendency could be seen using these two plots here. So, the top right one and then the bottom right one. So, the top left one and the bottom right one. So, in both these plots you can actually sense the tailing off tendency, alright. Now, again for a second, if you observe this plot which is on the top left, now again as x axis gives you all the lags, so let us say 1, 2, 3, 4 etc. So, I can actually conclude that such a plot is showing a tailing off tendency after lag 2, and then the exact same thing could be seen in this plot here which is on the bottom right, okay. So, again just to summarize this entire idea about how do you fix particular orders for a ARMA model using ACF and PACF plots is to draw both the plots and conclude using both the plots, alright. So, one should not jump to conclusion only based on a single plot, either ACF or PACF, right. So, always if you are analyzing any practical data, you should make this habit of drawing both the plots simultaneously, ACF and PACF, and then observe the patterns and behaviors of the correlations which are happening in both the plots collectively, right. So, if in one of the plots if you are showing a cutting off tendency and in the other plot if you are seeing a tailing off tendency, then accordingly you can choose the model to be either AR or MA, and then after what lag are you seeing the cutting off tendency, that sort of fixes the order. Make sense so far, alright. Okay, so this idea is entirely based on collection of let us say AR plots, MA plots, right, and the corresponding ACF and PACF plots for these two models. So, particularly AR model and then MA model, okay. Okay, so apart from ACF and PACF plots, you have several other criteria or several other techniques to kind of identify the models, alright. Now, I will tell you one disadvantage of ACF and PACF plots, okay. So, for example, besides ACF and PACF plots, we actually have multiple other tools for model identification, right. Now, again just to summarize, this entire idea about model identification is nothing but identifying the orders. So, identify the orders of the model, alright. So, if you keep this one statement in mind, that what are we discussing basically, right. I mean, what is the role of ACF plot and PACF plot really is to identify the appropriate orders of the underlying model. So, let us say ARMA or even ARIMA etc. Okay. But what happens is if you have a really large and messy data, right. So, let us say if you bring in a very heavy kind of a practical data containing lot of features and then lot of repetitions, right, then what happens is ACF and PACF plots become complicated and harder to interpret. So, in such a case ACF and PACF plots may not show the exact tendencies that we saw earlier. So, let us say cutting off or tailing off etc. Okay. And this could be a disadvantage, right. So, if you bring in really heavy kind of a structured data which would be kind of messy and really large, then probably basing or identifying the orders from ACF and PACF plots becomes difficult. Okay. And here the last point is, since many different models can be fit to the same data, right. So, let us say if you bring in some practical data, you plot the ACF and PACF. Now, based on after what lags are you seeing the cutting off and the tailing off tendencies, I can actually have slightly different models also in mind, right. For example, let us say you are seeing cutting off and tailing off tendencies after lag 2 in both the ACF plots and the PACF plots. So, one possible model in our case could be let us say ARMA 2.2, right. But here people or practitioners can play around slightly. So, what do you mean by play around? So, let us say ARMA 2.2, if they think that this might not be the model, they can actually play around slightly with the order. So, let us say 1, 2, or they can actually look for fitting something like ARMA 2, 1, right, or even they can actually think of fitting something like ARMA 1, 1, right. So, again just to understand that even though you are basing conclusions using the ACF and PACF plots and then after what lag are they cutting off or tailing off, but then this may not be the 100% correct model, right. So, for that you have to play around with the orders slightly, right. So, here playing around only means that you kind of take orders which are in the neighborhood of, let's say, 2, 2, right. So here I am not saying that one should actually look for something like ARMA 6, 6, right, because 6, 6 is way away from 2, 2, which was seen from the plots, right. So hopefully this idea is clear. So since many different models can be fit to the same data, precisely all these, right, I mean you have a collection of models which you can actually try fitting on the data, but we should choose the most appropriate one having less parameters firstly, and the information criteria will actually help us to decide this, right. So once you kind of fixate a bunch of models or a handful of models, then you kind of go ahead and then find out the information criteria, which we will discuss soon, and then using the information criteria you can actually fix on one particular model, okay. Now firstly, what do you mean by a model having less parameters? So less parameters obviously means that, for example, ARMA 1, 1 would have lesser parameters than ARMA 2, 2, right, because if you have more orders, then eventually if you bring the ARMA equation in your mind, right, or in your head, so if you keep on increasing the orders on any side, so be it AR or MA, the number of parameters also increase in that case, right. The number of phi coefficients and the number of theta coefficients, they go on increasing. So in this case, ARMA 1, 1 would have a lesser number of parameters as compared to all the above models basically, okay. So one should not jump to conclusions based on, let's say, if you are seeing something like ARMA 6, 6 which is really good or the fit is really good, but you may be overfitting the data, right, because ARMA 6, 6 contains lot of coefficients here, right. So my point is, if the same job could be done using approximately the same accuracy, then you should always go with a model having lesser number of parameters. Alright, so now we will talk briefly about what do we mean by information criteria, and then how can you choose a particular model based on a set of information criteria, okay. Okay, so these are predominantly some of the famous or some of the important information criteria which people use. Now the first one is called as Akaike's information criteria, or in short we call it as AIC, right. So by the way, AIC, the first one and the second one are kind of more applied or more used as compared to the third one, okay. So by the way, this was introduced by a person called as Akaike back in 1974. Then similarly, the second one is called as Schwartz Bayesian criteria, or in short SBC, and again some people or some textbooks write it down as Bayesian information criteria, or BIC. And then this particular criteria was introduced by Schwartz, a person called as Schwartz, back in 1978. Okay. So Akaike's information criteria came slightly before than Schwartz, and then very soon we will see why, because Schwartz is a slight extension of AIC. And then the last one was brought by these two people, so Hannan and Quinn. So Hannan and Quinn criteria, or in short HQIC, and then these were brought by a couple of people, so Hannan and Quinn in 1979. So if you see the progression, right, I mean the first kind of a predominant information criteria was brought in 1974 by Akaike, then Schwartz kind of brought an extension to that in 1978, and then Hannan and Quinn kind of again extended Schwartz criteria and then brought another criteria in 1979. Okay. Now essentially what do you actually mean by information criteria? So all three are information criteria, but how can you apply them or how can you use them? Okay, so we will focus on the first one, which is Akaike's information criteria, or in short AIC. So assume that you have a statistical model with m parameters and you are trying to fit some practical data using that model. Okay. So again, how many parameters you have? You have capital M parameters in that model. Okay. So I can actually write down a short formula for finding the Akaike's information criteria, or AIC. So in this case, AIC is nothing but minus 2 into log of the maximum likelihood plus 2 into capital M. So in short, this is nothing but minus 2 log of my maximum likelihood function plus 2 into the number of parameters which are underlying in the model. Now again, here I am assuming that you should have some knowledge about maximum likelihood or MLE technique, right. MLE technique is nothing but an estimation technique, right. So if you are not very confident about what exactly you mean by MLE technique, you might want to revise slightly. Okay. So here essentially what we are doing is likelihood is kind of similar to a joint density, right. So let us say if you have lot of different random variables, So if you're working with the practical data, then how do you put forward a joint density combining all the observations? So that joint density is nothing but the likelihood. And again, the idea is always to maximize the likelihood as much as possible. Okay? And then the corresponding estimator that we get of the parameter is called as MLE, or the maximum likelihood estimator. Okay? Okay, so now we'll see that what goes on for a particular ARMA model. So let's say if you have an ARMA model with n observations, right, then we can actually write down the log likelihood using a pen and paper. So the structure of the log likelihood function actually becomes something like that. Okay. Now again, I will not go into too much detail, I will not show you or probably I will not prove as to why this is the log likelihood, but you require some assumptions. Okay. So what exactly are the assumptions? So we assume that this S function that you see in the log likelihood, which is right here, is nothing but the residual sum of squares. Now again, all these terms are coming from regression context also. So if you have taken a regression course, maybe sometime in your college days, or even university days and so on, or in your current degree that you are pursuing, if you have taken a regression course, then all these terminologies are kind of borrowed from regression. So what do you mean by residual sum of squares, right? So residual sum of squares is nothing but once you fit any kind of a model, so be it regression or time series, whatever, then you look at the residuals, right? So residuals are nothing but what exactly? So y minus y hat, right? So the actual value minus the fitted value. So this is nothing but the residual. And essentially what you're doing is you're taking the sum of residual square, something like that. Okay. So this capital S represents nothing but that. So residual sum of squares, assuming all my residuals or all my errors follow a particular normal distribution with mean 0 and variance sigma square E. So these are a few assumptions. Again, all these assumptions are kind of consistent if you are applying a regression kind of a technique or time series modeling kind of a technique, right? And then generally speaking, all these assumptions are put on the residual or the random error that you have in the model, which according to our notation is ET. Okay? And since we are assuming a normal distribution with mean 0 and variance sigma square E, the first part that you see here, right, in the log likelihood actually comes from the constant that you have in the normal density or the normal PDF. Okay? So again, like I said, we will not prove this entirely, but then just to give you an idea as to what individual ingredients you have here, right. So the first part in the log likelihood comes from the constant that you have in the normal PDF, assuming that mean is 0 and variance is sigma square E, and the second part, which is capital S of let's say phi p, theta q and mu, is nothing but the residual sum of squares. Okay. And here we are assuming an ARMA model, right. So ARMA model contains p number of phi coefficients, q number of theta coefficients, and if you have an intercept, there will be an intercept which is mu. Okay. So these are nothing but the set of the parameters, right. So essentially what is happening here is that you are applying some maximum likelihood technique to estimate all these parameters, the underlying parameters, and then once you estimate the parameters, we get hold of the residuals. So y minus y hat. So the actual parameter values minus the fitted values gives you the residuals, and then we kind of take the summation of the residual square, which you have here in terms of capital S. Alright. Okay, so again just to reiterate that if you have an ARMA model with n observations, the log likelihood function can be actually written down in this format, right. Then what? So let's say once you write down the log likelihood, then the next step is to maximize that, because you want a MLE or you want a maximum likelihood estimator. Okay. So after maximizing the log likelihood function, we actually get this. So AIC is nothing but n log of sigma square E hat plus 2 into m. Okay. Now again, why sigma square E hat? So why do you see hat here? Because this is nothing but the estimator of the variance, right. So since you are using an estimation technique which is MLE, so you can actually replace that estimator now in terms of variance. Okay. But essentially this is the AIC formula. So n into log of sigma square E hat plus 2 into the number of parameters you have. And here, regardless of whichever information criteria you pick, so be it AIC or SBC or Hannan and Quinn, the idea is always to minimize the particular information criteria. So similarly, pick the model or the particular value of m which sort of minimizes the AIC. Okay, so the goal should always be to minimize any of the information criteria that you have. Okay. Now, here one point I would like to make, that can you actually see that if you bring in different number of parameters, so bringing different parameters means what? So, you are kind of changing the orders of the ARMA model, isn't it? So, let us say if you have ARMA 2 comma 2 as discussed earlier, as compared to let us say something like ARMA 2 comma 1, then you will obviously have different number of parameters, right? And when you have different number of parameters, the value of AIC would also change, because this depends on this M here, alright. Then again the idea should be that pick a model out of these two, or let us say out of the 4 that we had earlier, which gives you the minimum AIC or the least AIC, alright. Okay, so this is the first one. Now we will talk briefly about the second one, which is Schwarz-Bayesian criteria, and then we will see that how this is an extension of AIC. Okay. So, firstly, SBC is a criteria for selecting models having different number of parameters again. So, similar to AIC, the idea is same kind of, that if you want to fit or if you want to try out different models having different number of parameters, right, then we can actually use some information criteria, let us say AIC or SBC and so on. But how exactly is this different? So, when estimating model parameters using a maximum likelihood estimation, it is possible to increase the likelihood by adding additional parameters. Okay. So, this is one problem that one can actually face, right. So, let us say if you keep on increasing the number of parameters, it is possible to increase the likelihood, and if you keep on increasing the likelihood, so we will get higher and higher MLE. So, we are kind of reaching the maximum there. So, the estimators might be slightly better, right. But one disadvantage here is that which may result in overfitting also, right. So, let us say if you keep on increasing the number of parameters blindly, that would of course result in overfitting. Hence, the BIC kind of solves this problem. So, BIC or SBC resolves this problem by introducing a penalty term for the number of parameters that you bring in the model. Okay. So, the whole game here when you talk about either SBC or BIC is that it should contain an extra penalty term which kind of focuses on the number of parameters one can bring in the underlying model. Okay. So, now we will see the formula for SBC. So, this is the formula for SBC. Now, again the idea is the same, that you get hold of the likelihood, you take the log likelihood, you try to maximize that, right, and then this is the formula for SBC. So, n log sigma square E hat plus m log n. Now, again if you focus on this formula and the earlier, which is AIC, the only difference is this m log n is new here, and then in AIC this was nothing but 2m, right. But here can you now see that you are kind of giving a penalty term on how many parameters, which is nothing but given by capital N or capital M rather, one can bring in, right. So, if you keep on increasing this capital M, which means that you are bringing additional parameters, then obviously this term would go on increasing, because now you do not have a constant, unlike we had in AIC which is 2, but now you have log n, right. And then essentially speaking, log n is generally bigger than 2, of course for some n, right. But then since log n is generally bigger than 2, so it is kind of giving a penalty for any extra parameters that you bring in. Okay. And couple of other things, that SBC has superior large sample properties, and then SBC is consistent, unbiased and a sufficient kind of an estimator. Okay. So, people actually use either AIC or SBC when it comes to choosing a model based on some information criteria. Okay. And again, like we discussed, we will discuss very quickly the third one, which is HQIC or Hannan and Quinn. So, again as you see the formula, so Hannan and Quinn gives an extra additional term here. So, n log sigma square E hat is the same from AIC or SBC, but now instead of 2m or let us say m into log n, you have 2m log of log n, alright. So, again Hannan and Quinn has its own advantages or probably disadvantages when it comes to AIC and SBC, but as discussed, people kind of prefer either AIC or SBC because of simplicity kind of. Okay. Alright, now, so we actually have other techniques of model identification. So, one can actually look at something called as sample inverse autocorrelation function. Now, again we will not go into details, but then short form is SIACF, right. So, rather than ACF, one can actually have an inverse autocorrelation. So, if you have a model, you write down that model in terms of an inverse kind of a structure, and then have its correlation. Okay. And couple of advantages that such a correlation, which is SI-ACF, generally captures orders better in seasonal models as compared to, let's say, PACF or even ACF. Okay. And one very important idea here is that it is also useful for detecting over differencing. So, over differencing means what? That in one of the earlier lectures we discussed about this nabla operator, right. So, if you operate this differencing operator on yt, it actually gives you yt minus 1, and there we saw that one can actually difference a model or difference a time series multiple times. So, let us say nabla to the power d, something like that also, right. So, but then again if you keep on differencing unnecessarily, or the amount of differencing that you pursue is much more than the expected number of differencing, then using this SI-ACF kind of a function, it kind of detects that over differencing which is happening. Okay. Okay, so now probably in the next session we will kind of extend this idea, we will see some examples, right, and then possibly we will move ahead. Okay. Thank you.